There are lots of practical problems that can be formulated as problems in making some function as big or as small as possible. Like say, for example, that we are looking for the best dietary intake of some nutrient. So we make a plot and find that up to a certain point the benefit increases with increasing dietary intake, but eventually that stops happening. And after that, taking more of that nutrient might do more harm than good. Or suppose we want to maximize profit from production of some product and we find that profit increases with increasing production up to a certain point, and then machines start breaking down or we run out of customers or there are other trade-offs and profit goes back down again. In general, there is a function f called the objective function, and the goal is to maximize that function as a function of some variable x. The problem is solved by coming up with a formula or some other way of calculating the objective function. In this case, the formula is just 100x minus x squared, and then finding the maximum of that function, which can be done in this example using the maximize function. The maximize function returns a list giving the maximum value of the objective function and the value of the variable x at that point. There are many variants of this sort of thing. Often there is more than one variable or even hundreds of variables. Here's an example with two variables, maybe the settings of two controls on a device or the amounts of two ingredients in some process. And this time the goal is to minimize something, maybe minimize fuel consumption or minimize cost. The 3D plot shows the objective function as a function of the two variables, and the minimum can be computed using the minimize function. In practical examples, there are often constraints on the variables. Dietary intake of a nutrient cannot be less than 0, for example, or maybe the amount of some raw material is limited by the amount that is available. Constraints like that can be entered as inequalities. This shows minimization with the constraints that x has to be less than 1 and x plus y has to be less than 2. In this example, the minimum is at a boundary of the region defined by the constraints, which is pretty common since often the best way to do something is by setting some control as high or as low as possible, or by using as much or as little of some ingredient as possible, or by otherwise choosing values at the limits of the constraints. The region defined by the constraints is sometimes called the feasibility region. We can use the region plot function to get a plot of the feasibility region. The minimum in this example is at a point on the boundary of the feasibility region. The objective function is also often a lot more complicated, like this function, and the minimum or the maximum is most easily computed using numerical methods, such as by using the n-minimize function. And the n-minimize function can also handle problems with constraints. The minimize and maximize functions without the n use symbolic methods and give exact solutions, which is sometimes useful, but those methods can't handle this more complicated example, and the minimize function just returns the input. In addition to n-minimize, there is another numerical function called find minimum that can also do this calculation. The difference with find minimum is that find minimum is designed for finding local minima, while n-minimize is designed for finding global minima. Local minima can be an issue for examples like this one, where the objective function has several local minima. The different local minima can be found by giving different starting values in find minimum, and actually it's also possible to give starting values in n-minimize so that it too finds local minima, but the default behavior of n-minimize is to look for the global minimum. So now we have basically three ways of finding a minimum. There is the minimize function, which gives an exact solution, and the n-minimize function, which does the calculation numerically, and the find minimum function, which also does the calculation numerically. And in a simple example like this one, they all basically find the same minimum, which brings up the question of how to decide which function to use. And there are actually lots of other functions that haven't come up yet that are listed in the guide page on optimization in the Wolfram documentation. The minimize and maximize functions are useful for getting exact solutions to simple examples that can be solved symbolically. For bigger problems or for problems that can't be solved that way, the most general functions are n-minimize and n-maximize, which use numerical methods to look for a global minimum, and find minimum and find maximum, which use numerical methods to find local minima. These numerical functions take a method option that allows for choosing between optimization algorithms, which are listed in the documentation for each function. The methods used by n-minimize and n-maximize are methods for finding a global minimum or maximum, and the methods used by find minimum and find maximum are usually a little bit faster and are good for finding local minima and maxima. Several of the other functions listed in the guide page actually use those same functions and are there mostly for convenience. The min-value function, for example, just returns the first element in the result from minimize, so it's the same as applying first to the result from minimize. The rest of these functions are mostly designed for special cases, like find_fit finds parameters that minimize the distance between a parameterized function and some data, and there are other more specialized functions, like functions for solving the traveling salesman problem and the knapsack problem, which are classic problems in optimization. One function worth highlighting here is the linear optimization function, which handles the special case where the objective function and all of the constraints are linear functions of the variables, like in the following example where the objective function 3x plus 4y is a linear function of x and y, and the constraints are also linear in x and y, and there aren't any nonlinear things like x squared or e to the x. N-minimize and find a minimum can also do this problem, but the linear optimization function is faster. Optimizing linear functions with linear constraints is called linear programming. It's common practice in linear programming to omit the variables altogether and to instead just give arrays with the coefficients of the variables in the objective functions and the coefficients of the variables in the constraints. The linear optimization function can also handle problems specified in that form. For example, this shows linear optimization solving that same problem, this time with the problem specified using arrays of coefficients. The first argument gives the coefficients in the objective function, and the second argument is a list in which the first element is the array of coefficients for the variables in the constraint inequalities, and the second element is the list of constants in those inequalities. The solution is the same as before, it's just given in a different form. Algorithms for solving linear programming problems are fast and reliable and can handle problems with hundreds of variables, so it's common where possible to try to express optimization problems as linear programming problems to get those advantages. More generally, though, a good place to look when solving optimization problems in the Wolfram language is this guide page on optimization or any of various tutorials, including this page on unconstrained optimization and this page on constrained optimization.